Hello, I'm Alastair Donaldson. I'm a lecturer at the Department of Computing at Imperial College London, and this is the second of 3 lectures I'm recording about GPUVerify, a technique and tool for analysing GPU kernels which we've been developing as part of the CARP project. In this lecture, I'm going to start digging into the technical details of how GPUVerify works, showing you how a GPU kernel is translated into a sequential program to be analysed. So this is really the verification method. Before I start talking about the details, I just want to say that there's actually a lot of exciting work about GPU verification and analysis going on at the moment. So the University of Utah, the group led by Ganesh Gopalakrishnan, have some really exciting work going on. They were really the pioneers in this field with their PUG tool, which was published in 2010. And PUG and GPUVerify share many similarities, including the reduction to a pair of threads that I'm going to show you during this lecture. So I want to be clear that some of the things I'm showing you here, we use them, but they're not necessarily our original ideas. They're things that have been pioneered by others and extended by us. There's some exciting work from the University of Twente, also part of the CARP project, on permission-based separation logic as a means for verifying GPU kernels. And then there are a couple of techniques, one from Utah and one from colleagues here at Imperial, on analysing GPU kernels to find bugs using dynamic symbolic execution. And finally, there was a paper at last year's PLDI conference about combining dynamic and static analysis to prove race freedom of GPU kernels. So if you would like to find out more about these papers, you could go to the GPUVerify webpage, where there will be links to all the work that's going on in the community about GPU verification. And please let us know if you have any more work of your own that you would like to share. So what GPUVerify does is it actually focuses data race analysis on barrier regions, based on the observation that all threads executing a kernel, and by the way, during this lecture, I'm going to be thinking about threads that are in the same group rather than threads in different groups. The tool and technique do handle the intergroup case, but for the purposes of simplicity here, I'm not going to go into the details of that. So threads in the same group are always going to be executing between some pair of barriers. So say we have a first barrier and a second barrier and a barrier-free region of code, then at any point of execution, threads are either before the first barrier or after the second barrier, or they're in this barrier-free code region. And in particular, it's impossible for there to be a data race because of one thread executing before the first barrier and another thread executing inside this region of code, because the barrier actually means that this is impossible. The threads have to get to the barrier and then all proceed past the barrier. Of course, this is a little bit more complicated if barriers are nested inside loops, and our technique does handle that in full, but I'm not going to go into the details of that right now. So a race can only occur due to 2 statements in the same barrier region, and this greatly simplifies race analysis. We don't need to consider arbitrary pairs of statements in the whole kernel. We can actually consider pairs of statements in a single barrier region. So this is immediately something that gives us a handle on the problem we're trying to solve. All right, so the key thing here is that data race analysis is restricted to barrier regions. This doesn't help too much though, because if we've got n threads and we have k statements in a barrier region, so here we've got statements s1, s2 up to sk, then there are a large number of possible thread schedules for this barrier region if we assume that these statements are atomic statements. So actually, the total execution length of any interleaving is going to be n times k. There are n threads that each have to do k things. So in total, there are going to be n times k things that happen. How many ways can we interleave these things? Well, thread 1 is going to execute k statements, and there are n times k choose k choices for the way thread 1 could execute these statements. And then thread 2 is going to execute n statements, and there are going to be n minus 1 times k choose k choices for these, because k of the positions in this n times k sequence have now been taken by thread 1. So there are n minus 1 times k positions left, and thread 2 could take k of these. So there are a large number of choices for these k statements, etc., etc. Okay, and I'm not terribly good with combinatorics, but the number of possible thread schedules is in the order of n to the power k, which is going to be enormous if the barrier region has got many statements in it. So although we've restricted attention to this barrier region, which is better than focusing on the whole kernel, there could still be many thread schedules to consider within this barrier region. Do we really need to consider all of these thread schedules to detect data races? Well, actually, the answer is no. It suffices to consider just a single thread schedule. And in fact, it can be any thread schedule we like. So GPUVerify relies on this observation, which I'm going to justify to you in a minute. And this is an observation that has been made independently by several researchers. It's used in a variety of the techniques for analyzing GPU kernels, and also in various methods of doing partial order reduction for concurrent software. There are similar observations to do with if you guarantee detecting data races, you can relax the number of schedules you need to consider. So let me explain this in our context. Suppose we have a barrier A and a barrier B and some barrier-free region of code between A and B. What we could do is we could just let thread 0 run all the way from A to B. We could log all of the accesses thread 0 makes. So we know exactly where thread 0 read from, exactly where it wrote to. Then we could run thread 1 all the way from A to B, and we could log all the accesses thread 1 makes. And furthermore, we could check these accesses against those of thread 0. And if we find that thread 1 reads or writes from or to a memory location that thread 1 wrote to, then we can abort. Okay? And similarly, if thread 1 has done a read, we can check that if thread 0 has done a read, we can check that thread 1 doesn't write there. Then we can run thread 2 from A to B. We can log all thread 2's accesses, and we can check those against both thread 0 and thread 1. And we can continue this process, and finally we can run the last thread n-1 from A to B. We can log all the accesses it makes, and we can check that they don't interfere with any of the accesses made by preceding threads. If you think about this, because we're going to abort if we detect a data race, then either there is a data race that can occur between two threads, in which case the first thread will log its accesses, and when we check the second thread's accesses, we will find this data race. Or there can be no data races, okay, in which case there's actually no way the threads can influence each other between these two barriers. They can only influence each other by the actions they make between the barriers if there is a data race. So for instance, if thread 5 was going to write to some shared variable and thread 3 was then going to read that and make a decision based on its value, that would constitute a data race between these threads and we would abort. So if there are no data races, actually this schedule where we run thread 0 all the way, then thread 1 all the way, then thread 2 all the way, that schedule is just as good as any other schedule. The state of the kernel will be the same once we get to barrier B, no matter which schedule we choose. So GPUVerify exploits this trick. It in fact doesn't take this schedule of running thread 0 all the way, then thread 1. It uses a different schedule, which I will come to in a minute. So this is really good because it completely avoids reasoning about interleavings. And in fact, it lets us think about the GPU kernel as if it were a very long sequential program where we serialize the execution of the threads. So we have a long program because there are many threads, but we don't have to consider all of these interleavings. So because we could choose a single thread schedule, in fact, if there are k statements in our barrier region, we can reduce analysis to a sequential program representing this barrier region that has n times k statements, one statement per thread. Okay? I mean, for every k statements, we have a copy of those statements for every thread. This is good because we're back in the realm of sequential program analysis, which has been studied for many years and in which we've made great progress as a community. But in practice, as I showed in the previous lecture, we might have a GPU kernel that runs thousands of threads. So we're going to get a very long sequential program, which is going to be intractably large to analyze. So what can we do about this? Can we do better? Actually, yes, we can. What we could do is we could choose a pair of threads, I and j, in the range of thread IDs. And then we could consider this barrier interval, barrier A to barrier B, and we could run thread I, where I is just some thread, all the way from A to B. We can log all of the accesses I makes. And then we can run thread J all the way from A to B, and we can log, well, we don't need to log thread J's accesses. We can simply check that the accesses thread J makes don't interfere with the accesses that thread I makes, and we abort if we find that there is a data race, if there's an interference between the writes and reads of thread J with respect to the writes and reads of thread I. If you think about it, a data race is a pairwise property. It always occurs because of some pair of threads. It doesn't involve 3 threads or 4 threads. So there might be a race between, say, thread 5 and thread 17. And if we're going to prove that this barrier region is okay for all pairs of threads, that involves considering the pair 5, 17. And if there could be a race between them, we will detect it when we consider that pair using this trick here. So if we can show that the barrier region is race-free for every pair of threads, then we've actually shown the barrier region is race-free overall. The key thing here is that if a race exists, it must be because of some pair of threads. We're going to consider all pairs. I think this is quite a subtle point, and this is, again, a trick that's been exploited by various researchers and by the PUG tool. It takes a little while to wrap your head around. We do have a formal proof in one of our papers. Is it sound, though? Well, let's think. So suppose we've got a barrier A and a barrier B, and we pull this trick. We run thread I all the way from A to B, logging what it does, and then we run thread J, and we check its accesses in abort on raise. This is okay. We can now establish there are no data races between A and B. But let's suppose we now have another barrier region, B to C, and we now want to run this pair of threads from B to C. Is that okay? Well, actually, this is kind of problematic because it's as if we only have these two threads. They've updated the shared state. Then they synchronize it to barrier, and they should now be able to see what all of the threads executing the kernel did. But we don't have those threads, so if we now let I and J keep running, they're going to be reading from elements of arrays that would have been written to by other threads, but they're not going to see the changes that those other threads would have made. So, in fact, this is complete nonsense. So, this is not sound. It's as if thread I and thread J were the only threads running the kernel. We're not going to see the effects of other threads. So, a way to get around this is to make the shared state abstract. So, we say that when you read from the shared state, you get some arbitrary value back. And this arbitrary value reflects the fact that other threads could have manipulated the shared state in ways that are not visible to the two threads that are executing. And a very simple idea here is to havoc the shared state at every barrier. So we make the shared state arbitrary at every barrier. And this is what GPUVerify does. Or something even simpler, which I'm going to show you later in the lecture, is just to remove the shared state completely. And when you read into a variable, you havoc that variable. You make it non-deterministic. And when you write into the shared state, that could just be a no-op, because there is no shared state. So yeah, like I said, an even simpler idea is to remove the shared state completely. I'm going to talk quite a bit about this operation havocing. So if x is a variable, havoc x means set x to an arbitrary value. If you like, you could think about it as randomizing x, although havoc is an operation that is performed in a verification context. It's not something you would do in a running program, so I prefer to think of it as making x arbitrary, considering all possible choices for x. So the GPUVerify technique and tool exploits the any schedule will do trick, the two threads will do trick, and also this shared state abstraction to make the two threads trick sound, to compile a massively parallel kernel K into a sequential program P such that, roughly speaking, and I will explain later why this is only roughly speaking, if we can prove that the program P is correct, and by correct I mean that no assertions can fail in P, then we know that the program K, the massively parallel kernel K, is free from data races. And because we have a lot of techniques for analyzing sequential programs, in principle it should be quite easy to verify P. Of course, these sequential program verification techniques are far from fully automatic, so it is a challenge to analyze this program, but it's much less of a challenge than it would be to directly analyze a massively parallel program. The architecture of the tool is as follows. We take a kernel either in OpenCL or CUDA, and in future work, we would like to consider Microsoft's C++ AMP programming model, which has various similarities with OpenCL and CUDA. We take one of these kernels and we run it through a front end built on top of the Clang and LLVM compiler framework. So Clang and LLVM know how to parse OpenCL and CUDA, thanks to great open source efforts by other people. And they turn this into an LLVM control flow graph. And we have a tool that then translates that control flow graph into a Boogie program. So Boogie is an intermediate language for verification. So we have this kernel transformation engine component, which we've developed at Imperial, which takes the LLVM control flow graph and produces a Boogie program which applies this rewriting of the parallel program to a sequential program executed just by two threads. I mean, it's a parallel program executed by two threads with a fixed schedule, thus it is equivalent to a sequential program. So we have this sequential Boogie program, and we can reuse the existing Boogie verification engine to analyze that program. And Boogie calls out to an SMT solver, by default Microsoft's Z3 SMT solver, which is what the tool uses at the moment. And we're also looking into support for the CVC4 SMT solver as an alternative or a complement to Z3. Verifying a sequential program involves reasoning about loops, so we have a technique for generating candidate loop invariants, which I'm going to talk briefly about in the final lecture in this series. And a nice thing about this setup is that the Clang LLVM compiler framework is very widely used, extremely widely used, I would say. Z3 is very widely used in verification and other areas as a constraint solver for many projects. And Boogie is widely used as an intermediate language for various verification tools. So if there are bugs in Clang and LLVM, it's very likely other people will fix them for us, and they're constantly improving, similar with Z3 and Boogie. And the soundness of Boogie as a verifier has been well established for a long time now. So the only magic in our approach is in our kernel transformation engine. This is where we have to think very carefully and do soundness proofs to make sure that our argument for why verifying our sequential program allows us to conclude properties of our kernel, we have to make sure that this argument is sound and that there are not problems in our kernel transformation engine. But we don't have to worry about all the many intricacies of building a front end and building a verifier for a sequential programming language. What I'm going to do now is go into the details of how GPUVerify works reusing this infrastructure. I'm going to show you how this transformation into a two-threaded program is actually performed. And in the rest of this lecture, I'm going to focus on a kernel that doesn't have any conditionals or loops. This is just to make the explanation simple, and then in the final lecture, I will show you how conditionals and loops are handled. So suppose we have a kernel with the following form. It's got some number of parameters, which include some local arrays, some number of local variable declarations, and then a sequence of k statements. And let's assume that the statements have quite restricted forms. What we can do is we can have a statement x becomes equal to e, where x is a local variable and e is an expression only over local variables. Then we can have x becomes equal to a of e, where a is a shared array, so an array with a local keyword. It's a bit annoying that when you talk about a local variable in the usual sense, and then we talk about these local arrays which are really shared among different threads, but this is the OpenCL terminology which I'm trying to stick to. So A is a local array, that is, it's shared among many threads. And E is an expression purely over a thread's private variables. Or we can write into A at an expression E purely over private variables, and we can write the private variable X. And we can have a barrier statement. So let's suppose we have only these forms of statements. So just to reiterate, we have the restriction here that X is a local variable, E is an expression only over local variables, and A is one of the local array parameters, where local means shared among threads. So this restriction means that a statement involves at most one access to an array, a shared array. And this is easy to enforce by pre-processing the code. So we don't need to force the programmer to actually write their code in this way. We can easily pre-process complex expressions by pulling out the reads from these expressions. And it means that there's no conditional or loop code, which is a serious restriction. This would make the technique not very usable, but we're going to drop this restriction later once I've explained how things work. So what we want to do is to translate our kernel into a sequential program that models two arbitrary distinct threads executing, detects data races, and treats the shared state in an abstract way to make this sound. So we'll call the original GPU kernel K, and the program that we're generating we'll call P. So first we want to introduce these two arbitrary threads. So let's say that the kernel K has an implicit variable tid that gives the ID of a thread. So in reality this would be one of these built-in functions like getLocalID or threadIDX.x in CUDA. And let's suppose that n is the total number of threads. In our sequential program, we introduce two global variables that are ints. We introduce the variable tid$1 and tid$2. So I use $1 and $2 as a suffix to a variable name to say whether the variable belongs to the first thread or the second thread. Now we're going to consider two arbitrary threads. They don't have IDs 1 and 2 necessarily. They could have IDs 0 and 47. But I'm always going to call them the first thread and the second thread. So just to be clear, by tid$1, I don't mean the ID of thread 1. I mean the ID of the first thread that we are considering in our analysis. So we introduce these two variables to record thread IDs and preconditions on the kernel. So first of all, a precondition saying that tid1 is in the appropriate range of threads. So it's non-negative and it's less than n. And the same for tid2. And also a precondition saying that tid1 and tid2 are different from one another, so that they model distinct threads. Okay. Otherwise, the threads are arbitrary, so we're not imposing any ordering on tid1 and tid2. We're not saying tid1 is less than tid2. The threads are arbitrary, distinct threads within the thread range. Then we do some instrumentation of our arrays in order to perform race checking. So for every local array parameter A in the kernel, we introduce 4 global variables. We introduce a Boolean called read has occurred A. And this Boolean is going to be set to true if we are logging a read from the array A. And similarly, a Boolean write has occurred A will be set to true if we're logging a write to the array A. And then an int read offset A, such that if read has occurred A is true, this variable read offset A, this contains the offset that was read from. And an int write offset A, such that if write has occurred A is true, write offset A has the offset that was written to. And I will explain later how these variables are manipulated to perform race checking. And then we also introduce 4 procedures. Log read A, which takes an int offset, and it logs the fact that a read from A at offset was made. Log write A, which is similar. And then check read A, which takes an offset, and it checks whether at the time this procedure is called, it would be okay to read from A, that this would not cause a data race. And similarly, check write A. And I will show later on how these procedures are implemented to perform race checking. And then we actually get rid of the parameter A in P, because what I'm going to show you here is how we can completely abstract the shared state. So this array A is actually removed totally. So to illustrate what I've shown you so far, suppose we've got this form of a kernel. Kernel void foo. It has a local int pointer parameter A, so this is an array, a local int pointer parameter B, another array, and an int idx. So what we would do would we introduce tid1 and tid2. Then we would introduce a whole bunch of instrumentation variables. Read has occurred A, write has occurred A, read has occurred B, and write has occurred B. So these are Booleans to track whether we are logging a read from or a write to either A or B. And then read offset A, write offset A, read offset B, write offset B, which are ints tracking the offsets that were read from or written to. We would also introduce a bunch of these log and check procedures, which I'm not showing you on this slide. And then the kernel function foo is replaced with a regular function foo, where we have the idx parameter, that was a parameter to the original kernel function, but these array parameters A and B, these are gone. We're not representing them in the sequential program. And then we have some preconditions. So we have preconditions saying that tid1 and tid2 are distinct and are in the appropriate range. The next step is to duplicate local variable definitions in the kernel. So if we have a declaration of a local variable like int x, then what we generate in the 2-threaded program are 2 declarations, int x$1 and int x$2. So here we're saying that both of the threads under consideration have their own copy of the local variable x. So x$1 is the first thread's copy, x$2 is the second thread's copy. A non-array parameter, like idx in our example, also gets duplicated because every thread has its own copy of the parameter, and although those will initially have the same value, it's possible for a thread to update its parameter if it wants to, and this update is a purely local update. But we need to record the fact that these parameters initially had the same value. So if x was a parameter, then we have 2 parameters, x$1 and x$2, and a precondition saying that these parameters are equal, so requires x1 equals x2. And now I'm going to show you some notation. If we've got an expression over local variables and thread ID, E, then if we write E$1, what we mean is E, where every local thing, like a variable or tid, is replaced with the same thing $1. So for example, a local variable x would become x$1 if it occurs inside E, and we make E$1. And the same thing for E$2. This is actually a very simple idea that's best explained with an example. Suppose we had the expression E, which is A plus tid minus x. Then E$2 would be A$2 plus tid$2 minus x$2. So we're just propagating $2 into this expression. So this $2-arising of an expression allows us to actually transform the statements of a kernel into a round-robin schedule where the first thread executes a statement, then the second thread executes a statement, then the first thread executes a statement, then the second thread executes a statement, and so on. So this is a little translation scheme. If we've got an update, local variable x becomes equal to local expression e, this is trivial to translate. We say that the first thread does this update to its x with respect to its take on e. So we have x$1 becomes equal to e$1. And then the second thread goes, we do x$2 becomes equal to e$2. So this is a very straightforward transformation. Then if we have a read from the array A at expression E into local variable X, what we do is we first call this procedure log read A. And in our race checking instrumentation, which I'll come to in a bit, we're going to consider the first thread to be the logging thread and the second thread to be the checking thread. So because the first thread is the logging thread, we call log read A, and we pass in $1 as the offset that was read from. Then we call check read A, and because thread 2 is the checking thread, we pass in $2 as the offset that is read from for thread 2 to be checked. And then, because we don't actually have A anymore in our sequential program, we need to reflect the fact that X has changed, but because we've discarded any information about A, we need to consider anything that could possibly have been in A. So what we can do is we can simply havoc X for both threads. So we can havoc X for the first thread, and we can havoc X for the second thread to say that X becomes arbitrary. Just as an aside, it would now be legitimate to assume that X1 and X2 have the same value, okay? If you think about it, because we're going to detect data races, there's either a data race or they read from the array. Actually, no, that's complete nonsense, because $1 and $2 may lead to totally different offsets, okay? So they're not reading from the same index in A. So we have to havoc X separately for each thread to make it arbitrary for each thread. So forget what I said about assuming these things are equal afterwards. So this over-approximates the effect of reading from A to reflect the fact that A could have changed arbitrarily because there are actually many more than 2 threads executing this kernel. Just to reiterate this, because it's an important point, we remove the array A, so we need to over-approximate the effect of reading from A by havocing the receiving variables. Now let's consider the case where we would write to an array A at offset E, and we would write the local value X. So what we do here is the first thread is the logger, so we call log write A with the parameter E1. And then because thread 2 is the checking thread, we call check write A with the parameter E2. Now what do we have to do to reflect the fact that we've written to this array A? We don't have the array A anymore, we've discarded it. So actually, we don't have to do anything. When we read from an array, we havoc the receiving variables because anything could be in A. And when we write to an array A, we just do nothing. We don't write because there is no array to write to. And if you think about it, this is a sound over-approximation of the array. And then finally, we have this barrier statement, and we translate this into another call to barrier, but later in the presentation I'll show you that barrier is interpreted with a special meaning. If we have a sequence of statements, we translate the first statement and then the second statement. So that's the translation rules. Let me illustrate them with an example illustrating the concepts so far. So what we do is we have this kernel void foo function with a local int pointer parameter A, so this is an array. And we generate a regular function foo with a precondition about tid1 and tid2. And we would also generate these instrumentation variables for A, which I'm not showing on this slide. And then we take the non-array parameter idx and we duplicate it. So we have idx for thread 1 and idx for thread 2. And we don't put this array parameter A into the sequential program version of foo because we remove this array. And we had a precondition saying that initially these parameters idx1 and idx2 are equal. Then the local declaration x turns into two declarations, x1 and x2, similarly for the declaration of y. Now, the read from A tid plus idx into x, what we do is we call log read A, and we take this expression tid plus idx, and we $1 it. So we $1 it to get tid $1 plus idx $1. Then we call check read A with respect to the second thread, the checking thread, and we pass in tid $2 plus idx $2. And now to reflect the fact that we read from A into x, we havoc x. We havoc both copies of x. We havoc thread 1's copy and thread 2's copy. So x is now arbitrary for both threads. The write, then we have another read. We're reading from A tid into y, and this is similar. So we log read A for tid 1, we check read A for tid 2, and then we havoc y for both of the threads. And finally, we have a write at A tid, and we're writing the expression x plus y. So what we do here is we call log write. Thread 1 is the logger, so we are writing to the expression tid, so we log a write to tid 1. Thread 2 is the checker, so we check a write at tid 2. And then we don't have to do anything to reflect the fact that A has changed because we've removed A. So this example shows how we instrument the program to perform race checking. And now what I need to show you is how we actually implement these procedures, log read A, check read A, etc., so that race checking is performed. So we have these global variables, read has occurred A, and read offset A. And we use these variables to collectively log either nothing, if read has occurred A is false, we're saying we're not logging a read from A, or to log the offset of a single read from A by the first thread. So what does this look like? Okay, well, if read has occurred as false, then we're saying that there has been no read from A, in which case it doesn't matter what read offset A is. We're saying there is no read, and that offset variable, its value doesn't matter. If read has occurred A is true, then we're saying we are logging a read from A, and read offset A says the offset of the read that we're logging. So this maybe doesn't seem very satisfactory because there could be many reads from an array, and we're actually only providing the facility to log a read from the array A. Write has occurred A and write offset A are used similarly, by the way. But let me show you how this works. The log read A procedure takes an int offset. And what it does is it uses, well, what it could do is it could just say that we're logging a read, so read has occurred A becomes true, and read offset A becomes offset. But the problem here would be, suppose we had a bad read that's going to race with something later on, and then 3 good reads. What we would do is we would call log read A, we would log the bad read, then we would call log read A and we would overwrite the bad read with a good read and do the same thing again and again, and then we would miss the race between the bad read and a statement later on in the kernel because we've overwritten that read. So it's no good to implement log read as shown here. What we need to do is something a bit more sophisticated, which is we wrap these assignments in a non-deterministic conditional. So this star is a non-deterministic expression that evaluates non-deterministically to either true or false. So we're saying if star, so if we choose to, log this read. If we don't choose to, keep logging whatever we were already logging, if anything. So now, we are going to, if we have a sequence of reads, like bad read, good read, good read, good read, there's one resolution of a non-determinism where we, for instance, choose to log the bad read, we then choose to overwrite this by logging one of the good reads, and then don't choose to log the other ones, and then we won't detect a problem with the bad read because we overwrote the details of that bad read. However, there is a resolution of non-determinism where we choose to log the bad read, we don't choose to overwrite it with any of the good reads, and then we will detect a problem of this bad read with respect to a future read. So this non-deterministically choosing to log something means that at any point we will be logging some read that has happened in the past. And if we consider all program executions, we will consider all possible reads we could have logged. So this race instrumentation, this idea of using non-determinism in this way, I think is quite well known in the verification community, but it first was suggested to me by a former colleague of mine, Philip Rummer, who's now at Uppsala University. We published some papers together about doing race analysis for the cell processor, and we used a similar instrumentation to log data races. So thanks, Philip, for this idea. Like I said, star is an expression that evaluates non-deterministically. So we non-deterministically choose to either log this read from A, in which case the existing values of read has occurred and read offset are overwritten, or we ignore this read from A and keep logging whatever we were already logging, if anything. Log write A is completely similar to log read A. And then check read A is quite simple. So we're checking a read from A by thread 2, because remember thread 2 is the checker, and the read is from offset. So what we do is we assert that if the write has occurred A variable is true, i.e. if thread 1 has decided to log a write, then the offset we are reading from is not the same as the offset that thread 1 wrote to. So thread 1 has logged some write in the past to A, thread 2 is now doing a read from A, and we're checking that the offset being read from now is different from the offset that was written to in the past. If it's different, that's okay. If it's the same, then there is a read-write data race. Okay, so a read from A at offset by the second thread is okay unless the first thread logged a write to A at this offset. And this write has occurred A Boolean tells us whether or not thread 1 did log a write. And then write offset tells us the offset of the write that was logged. Check write is similar but slightly more complicated because if thread 2 is writing to offset, then it could potentially race with a former write by thread 1 or a read by thread 1. So we have to assert that if thread 1 logged a write, then the written offset is different from the offset being written to by thread 2. And we also have to check that if thread 1 logged a read, then the offset read by thread 1 is different from the offset now being written to by thread 2. So this is similar to check read, except there's a little more to check. We have to check for both reads and writes by the first thread. And initially, we need to say that no reads or writes are logged. So for every array, we need to insert preconditions saying that read has occurred A is false, if A is the array name, and write has occurred A is false. So we do this for every array. So here's an example, including the precondition. We've got the threads tid1 and tid2, the thread IDs being in range and different. We've got the parameter idx being different for the two threads. And furthermore, we've got no read having occurred from A and no write having occurred to A by thread 1. And then this is the code I showed you before. What we can do now is we can restrict this just to consider the log and check calls to see how these calls are interacting, because this example is very simple and actually the local variables x and y are not relevant because they just get havocked. Okay, so let's look at these log and check calls. And let's think about what the kernel looks like if we inline these calls. So we've got a log read A with the parameter tid$1 plus idx$1. So what this becomes is non-deterministically decide whether or not to log this read. And if we do decide to, set read has occurred A to true and read offset A to tid1 plus idx1. Then there's a check read A, and we're checking thread 2's read. So we're saying, is it okay for thread 2 to read from tid2 plus idx2? So this becomes an assertion that if a write has occurred to A by thread 1, then the write offset is not equal to the sum of tid2 and idx2. And then we can similarly inline the remaining calls. So I'm just taking the implementations of these procedures I showed you a few slides ago and inlining them with the given parameters. Now, the key thing here is that because we are using non-determinism, we ensure that there will be some program execution that will expose a data race if it could exist. So let's consider, for instance, the read from A at tid1 and the write to A at tid2. This pair of statements are clearly race-free because tid1 and tid2 are different. Will a race between these statements be considered? Yes, it will, because, for example, there's going to be a trace that will go through and choose to go in to this non-deterministic branch and log the read from A. And then the execution will continue. It will not go in here, and then it will assert that if a read has occurred from A, which it has, because we set this to true, then the read offset is different from tid2. And because the read offset was tid1, and tid1 and tid2 are different, which comes from the precondition of the kernel, then this assertion succeeds. So this is an example of a data race being checked, and the race is, well, there is no race, a potential race being checked and found to not be a race. But now let's consider the case where there's a read from A at tid1 plus idx1, and then a write to A at tid2. So there is a program path that will go in here, set read as occurred A to true, and set read offset A to tid1 plus idx1. Then these assertions will pass, and there will be a path that doesn't choose to go into these non-deterministic conditionals. And then finally, we get to this assertion, and we say, has there been a read from A? Yes, because we set this variable to true here. Okay, well in that case, read offset A must not be the same as tid2. Read offset A is tid1 plus idx1, and we have no constraint on idx1. So in fact, there will be an assignment to idx1 such that tid1 plus idx1 is equal to tid2. For example, if tid1 was 0, tid2 is 1, then setting idx1 to be 1 would cause a data race to occur. Okay? But the key thing is that because the verifier has to prove that the program is correct for all possible executions, it will consider all resolutions of non-determinism, and the scheme has been designed so that there is a case that will consider every pair of statements. So the final thing to show you for the instrumentation of loop and conditional free programs is how to implement barrier. And this is actually very simple. What we want to do with the barrier is just say that there are no reads or writes live anymore. We want to clear them. And what we could do is we could assign all of the write has occurred and read has occurred variables to false to clear any assignments where they were made true. Another thing we can do, which is actually very good for technical reasons, is we can simply assume that they are false. So an assume statement causes execution to block unless the condition is true. So any execution that has gone into one of these non-deterministic branches and set one of these read has occurred or write has occurred variables to true will be blocked by an assume that assumes that variable is false. However, we always guarantee there is one path that doesn't log anything. So there's always one path that never sets these variables to true, the path that doesn't go into any of the star-guided conditionals. So by assuming that a read has not occurred for A and a write has not occurred for A, and by doing this for every thread, by doing this for every array, we eliminate any path that logged a read or a write and essentially clear these sets. So for those of you who are really into verification, the technical reason why this is nice is that it stops these instrumentation variables becoming part of a loop's modified set simply because there's a barrier inside a loop. If we assign these variables to false, they would become part of the loop mod set, and then when we have a loop invariant, we would need an invariant to recover the values of these variables. That's the end of this part of the lecture, and in the next lecture I'm going to show how barriers are handled and how loops and conditionals are handled.